Okay, very good. Yes, welcome everybody. Thank you for joining. Um, today's presentation, we're fortunate to have John Brittis join us. John is he's a member of INCOSE, of course. John's currently a semi-retired engineer. He has degrees in physics engineering, nuclear engineering, and systems engineering. Um, John he's a registered professional engineer and project management professional and a CSEP, so a certified systems engineering professional. He's an expert contributor to the ISO working group that's currently developing standards on resilience, and a co-chair, is it, John, with the resilience working group in COSI. John has worked in the nuclear power industry where he has specialized in radiation safety. He's worked in the IT industry where he focused on artificial intelligence applications for complex engineering decision making, and in the systems engineering consulting arena, where he has supported aerospace and Department of Defense activities, again, focusing on system resilience. John is the past chair of the Resilient Systems Working Group, and again, as I said, currently the co-chair. So today's presentation is entitled Resilience and Loss-Driven Systems Engineering, or LDSE. This presentation is going to lead very well into our next presentation by Lou Wheatcraft on February 10th. If you do want to review this content before the February 10th presentation, this presentation, as all of our presentations for the INCOSE Canada chapter, are recorded and saved on the INCOSE Canada website where you can access them. So without further ado, I'm going to turn it over to you, John. You're sharing your screen already. I'm going to turn off my camera, and you can take it away. Thank you, John.
Okay, thank you very much, Ivan. And yeah, thank you for the opportunity to share some of the work we've been doing. Let's see. I'm going to talk about both resilience and loss-driven systems engineering in light of the fact that I'm kind of acting as an opening event for Lou Wheatcraft's presentation. I'll try to focus a little heavily on resilience requirements, and they are interesting. I think you'll learn a few things as we. Now, let me see if I can. Forward. Okay, to begin, I'm going to bring us all back to ground zero. We're going to talk about what a system is. And we all know a system is where you put together a bunch of elements in a particular configuration and magic happens. You get a capability that the system can provide that the individual elements cannot. And it's that capability that gives the system value to the stakeholder. And we will come back to that concept during the evening. But we know that a system does not live in isolation. It lives within environmental conditions. And a lot of the design for a system is based on nominal conditions. But you know, sometimes the system is having a bad day. Sometimes the environment is very hostile. Sometimes there's adversity trying to degrade the system. And resilience is all about how well the system delivers the desired capability in the face of adversity. And I'll use that word a lot. Adversity, for the purpose of resilience, is anything that can degrade the desired capability of the system directly or indirectly. And we'll come back to that issue of directly and indirectly a bit later. Now, there are many, many different definitions of resilience out there. A number of them are good, a number of them are really bad. The working definition that we've settled on for the Resilience System Working Group, which we believe is a good systems engineering definition, it supports systems engineering, is that resilience is the ability to deliver required capability when facing adversity. And that begs the question of, well, what's the scope of how you can achieve resilience? Because that is debatable. And we believe that the scope of resilience should include the ability to avoid adversity, withstand adversity, and recover from adversity. We know very well, some people think resilience is limited to just withstanding. Some people think it is limited to just recovery. We believe that for an engineering perspective, we need to consider all possibilities, and that includes avoid, withstand, and recover. And from the abstract I've seen, Lou is going to pound that into you next time you meet. Uh, One other thing I'd like to foot stomp is the objective of resilience is the required capability, not the system stasis or the system integrity. It's possible that the system may actually sacrifice part of itself to continue delivering required capability, or the system may evolve and change and adjust in order to continue delivering required capability. So the thing you have to focus on is the required capability, not the stasis of the system. Finally, I would like to point out that resilience does apply to all engineered system types, cyber-physical systems, organizational systems, and conceptual systems. The majority of what you'll find in INCOSE is about the cyber-physical, but for example, in the CBOC section on resilience, I prepared a section on organizational resilience, and that is in the CBOC. And I know, Ivan, you mentioned that you're active in the organizational working group. You might be interested in checking out what we say about organizational resilience in the CBOC. Okay, now I gave you the definition of resilience. It's the ability to deliver required capability in the face of adversity. But for those of you who, like me, think graphically, let me show you what that looks like on a diagram. A system is something that by definition delivers capability. And the acceptability of that capability is judged against the required capability. So there's the delivered capability, and it has to meet the required capability. And resilience is all about what happens if there's an adversity that stresses the system and can degrade its ability to deliver capability. This is what it's all about. This is the conceptual foundation of resilience. You'll see all of these terms show up a number of times as we move forward. Oh, and by the way, stress, I snuck a new term in there. Stress, we found, I earlier said, the adversity can be direct or indirect. From an engineering perspective, it's valuable to know what the direct adversities are, those that actually hit the system, not those that are back in a causal chain that lead up to the adversity that stresses the system. And stress is the term that engineers use to talk about a force or influence that affects the system. So we refer to stress to identify the direct adversity impacting the system. Okay, resilience parameters are dynamic. One thing that makes resilience a little complex is the fact that the various critical parameters can change as a function of time. And to demonstrate that, I'll plot capability on a vertical axis against time on a horizontal axis. The entire time being considered is the scenario period of interest. And so very frequently to evaluate a resilience situation, you need to decide what period of time, what scenario are we going to be considering. And now let's take a look at one of those terms. I mentioned required capability earlier. I'm plotting that here against time, and you'll notice it's decreasing because the required capability may change as a function of time during a scenario. I'll give you just one example. Let's talk about an air war. During the first 24 hours or so before you get air superiority in an air combat situation, you need a lot of communication bandwidth. You really do. But once you have air superiority, the demand, the required capability for bandwidth goes down. And so that's just one simple example. Another one would be the delivery of electricity to homes. You know, the delivery required goes through a 24-hour cycle, peaking in the midday and bottoming out at midnight each day. And so it's important to evaluate resilience. You need to be able to project what the required capabilities as a function of time. That's also true about the stress. A stress, it can be a single hit, it can be multiple single quick hits, or it can be a long and drawn out stress that varies as a function of time. And here we're showing that notionally. in order to evaluate resilience, you need to be able to model the stress applied to the system as a function of time. And now finally, the third thing is the delivered capability. And here I'm showing the delivered capability starting out at a nominal level. The stress starts to have an effect. The delivered capability starts to degrade. It actually goes below the required capability, but then there's a turnaround. The stress has ended and the system is starting to repair one way or another and comes back up, and it may come up, it can be a very complex function of how the delivered capability is restored. But the point of all of this is one of the complicating factors about resilience is it's usually got to be evaluated over a scenario time period, and various parameters change as a function of time, just to make the world complex. Okay, I don't need to mention that. Now, okay, we're going to talk about resilience requirement patterns for a moment. This came out of work that I did back in the 2019 timeframe. We were doing work. I was working for MITRE Corporation. I was doing work for the systems engineering leadership at the US DoD. And they came to MITRE and they said, hey, our guys are having trouble writing resilience requirements. Can you help us out with that? And it came down to me to respond to that. And I immediately went to the Systems Engineering Handbook and the various publications of INCOSE. And you know what? The guidance you get there is that requirements are a text. They're a box that you put text into. That's what SysML tells you. A requirement is a text item. They do not provide you any guidance in terms of what the content or the structure of a quality resilience requirement should be. And so anyhow, we did a very serious study. We did both an inductive and a deductive evaluation, and the good news, the inductive, we looked at about 14 exemplar requirements that were real requirements from the real world. And then we did a deductive evaluation based on just the theoretical thinking about resilience. The good news is they both came to the same resultant pattern, and that's what I'm showing you right here. The things that are in purple are where you fill in the blanks. And so the way this would read, and this is a pattern for a resilience requirement, the system, which can be in a particular mode, which can vary as a function of time, and a particular state, which can vary as a function of time, encountering an adversity, which can vary as a function of time, which imposes a stress that can vary as a function of time, thus affecting the delivery of the capability of interest. And that has a capability metric and a required capability, which can vary as a function of time, during a scenario time frame and under scenario constraints, shall achieve the resilience target for the resilience metric. And we could spend an hour easily talking about the ins and outs of this, but let me point out the thing that makes resilience requirements a little more complicated than your average requirement is your average requirement just says the system shall do X. Well, the resilience requirement is about how well the system shall do something, and that something is a capability which is based on another requirement. And so the resilience requirement is a compound requirement. It's a requirement about a requirement, and that's why you've got so much information that has to be included in the resilience pattern. And I'm sure Lou will go into this in further detail. I would like to mention, I don't think I've got it. Well, let me check. Oh, I do have it here. One thing we did in that study, we realized that different people need different forms of information. And so what I just showed you was the natural language form of the requirement pattern. We also created a data-based entity relationship representation of the same information. And that's what you're looking at right here. And so the exact same information can be delivered in the form of a natural language form that your average human being can read and understand and either agree or disagree with. It can be captured in a data structure, And we also developed a SysML extension that captured the exact same information. And so you could actually have the information residing in 3 different forms to satisfy 3 different communities. And I think that was pretty important. People have told me they like that. They like it a lot. Okay, now I'm going to shift gears. We're going to move away from requirements. I'm going to tell you a little bit more about what valuable stuff the Resilience System Working Group has put together. One thing is we have been curating a 3-layer taxonomy about the objectives and techniques for achieving resilience. The top level of that taxonomy is what we already talked about. The 3 fundamental objectives of resilience are to avoid adversity, withstand adversity, and recover from adversity. Now, the second layer are means objectives. These are not ends in themselves, but they are things that may help you achieve those fundamental objectives. And let's just take a look at them. I'll just read them off quickly. They may be that you want to be able to adapt, you may want to anticipate, constrain, continue, degrade gracefully, disaggregate, evade, evolve, fortify, manage complexity, minimize adversity, minimize faults, monitor, preserve integrity, prevent, reduce vulnerability, repair, replace, tolerate, or understand. And given the time we have tonight, we really can't go into that any further. But these are the types of things that you would consider at the high level requirements definition phase. Now, when you get to the actual design phase, that's the 3rd layer of our taxonomy. And I won't even try to read through these, but these are the architecture, design, and operational techniques that can achieve resilience. This is the toolkit that an engineer should work from when deciding what design technique should I try to apply to achieve resilience. And once again, because of time, we can't go into this any deeper. These show up a bit in the Systems Engineering Handbook, and they show up in more detail in the CBOC. So if you're interested in this, I would just go straight to the CBOC and take a look at what's in there. All of these are defined. Many of them have examples and so on. Okay, one other thing that's a little interesting about resilience is I mentioned earlier in the pattern, there are resilience metrics. And the question is, okay, what should the resilience metric be? It turns out they are highly situational. And examples are, that the metric might be the maximum degradation. How much did you degrade the voltage being delivered to the home? Or the period of degradation, how long was the blackout? And so on and so forth. And this is a list. We held I guess you could call it a symposium about 10 years ago. We brought experts from all around the country together and talked about resilience metrics. And these were the ones that floated to the top in terms of being the most useful. And at the time, I was working for a 4-star general at AFSpace, the U.S. Air Force Space Command. And I told him, sir, for this particular thing, we've got to have at least 3 or 4 metrics. He smiled and shook his head and he said, no, John, we're going to have 1 metric and you've got to pick it. And it turns out if you had to pick one best metric, that would be at the bullet at the very bottom of this slide. It would be the expected availability of the required capability. And that's the best one because it's based on the definition of resilience. And by the way, this is not just words. We define this rigorously and mathematically. And if you're interested in that detail, you can go and find the paper that's noted at the bottom of this slide. It's available on academia and ResearchGate and Google Scholar. And it defines exactly mathematically what it means to say the expected availability of the required capability. And we have applied this in the real world many times. It's a really, really decent metric for resilience. But, okay, and I'm doing pretty well on time. I do need to emphasize that the resilience metric you choose has to be about the needs of the stakeholder. And let me give you an example. Let's say that you're talking about delivery of electricity to homes. One important metric would be the length of a blackout. And you need to identify an appropriate target for how long that blackout can be. And so the metric is the length of the blackout, and the target for that metric, I could notionally say, should be 4 hours. And why would you make it 4 hours? Well, you would make it 4 hours because after 4 hours, the food in the freezer of people's refrigerators can start to melt and become unhealthy to eat. And that's how you have to figure out your metrics. You need to figure out what the end value is to the stakeholder, and base the metrics on that. And that is what has to go into your requirements for resilience. Okay, I'm going to shift gears and shift over to loss-driven systems engineering. Pardon me. And loss-driven systems engineering, if you haven't heard of it, stick with me for a few slides. I think you'll get it immediately. But ultimately, it's about facilitating systems that both do no harm and safeguard assets. And I'll explain all of that in the next few slides. LDSE facilitates systems that do no harm and, as appropriate, safeguard assets of interest. It identifies the transdisciplinary and integrative practices that apply to engineering disciplines that address potential losses associated with systems. So what are those disciplines that address potential losses? Well, those include resilience, safety, security, operational risk, CIPR, environmental protection, quality, availability, and we could probably name a few more. The bottom line is, while systems are normally all about delivering a capability that's desired by the end user, these are about safeguarding assets and minimizing or managing loss. And that's why it's called loss-driven systems engineering. And we'll come back to that, and I think it'll make sense within another 2 slides. Now, LDSE safeguards against loss of values of interest, and that's what we called assets. An asset is anything that is of value to the stakeholder in the face of adversity. So this is, you can tell this is not that much different from resilience, but it is. There is a difference between safety and security and resilience and so on. But we don't have time to go into that thinking tonight. Right now, we're working on this within INCOSE in the LDSE project, which is under the FUSE initiative. And I'm just going to let you know, this all got kicked off about 2017 timeframe and go down to the very, and it's been bouncing around INCOSE for the last 6 years, 7 years. And the main point is the bullet at the bottom. INCOSE LDSE project was authorized and initiated under FUSE in March 2025. And we're very well along in generating an LDSE handbook. And if things don't go south, we will be delivering that around mid-year in 2026. Now, what are some of our objectives? Well, we're developing working definitions of the various specialty areas, those disciplines that are loss-driven, like security and safety, and we're doing that so we can talk about them and have a general idea of what the boundaries are. But that's not that important, because we're trying to find where they share things, not necessarily where the exact dividing lines are. We're developing a harmonized common vocabulary so that all those disciplines can talk to each other effectively. We're developing a formal SysML conceptual foundation that can be shared by those disciplines. We're identifying common principles, tools, methodologies, and means toward achieving shared loss, and these include shared loss scenarios, shared requirements, shared modeling, shared analysis, shared design solutions, and shared risk management, because for any of those, it's very common for what safety wants to do It can be identical to what resilience would want to do and what security would want to do. And if they work together, they can be more effective than if they work as silos. We're also identifying the transspecialty area. Let me just say, that's very poorly worded. I need to rewrite that. We're going to be providing input for the next version of the Systems Engineering Handbook. We're developing the LDSE guide. We will be updating the CBOC. And ultimately, there may end up being a loss-driven enabling domain in INCOSE, tech ops. We'll see where this goes in the future. Now, to clarify the meaning of loss-driven systems engineering, I'm going to come at it from a slightly different direction. Please consider the definition of systems engineering. And I'm only really going to look at the first line or two. Systems engineering is a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems. And I'll just stop there. Transdisciplinary and integrative. Transdisciplinary points to the items that are common across all the engineering, and integrative relates to those things that can be shared and where there's commonality and a synergy among those disciplines. And here are some examples of the commonalities and synergies. The commonalities can include the common assets of interest, safety, security, and resilience, maybe thinking about the same assets, the common types of loss, the common adversities, the common loss scenarios. Potential synergies include shared vocabulary, shared modeling and analysis, shared requirements, shared architectural solutions, shared design solutions, and shared risk management. Now, once again, I'll try to represent what I've been talking about graphically. LDSE's relationship to systems engineering. Well, first of all, systems engineering practices. Those are those common practices that apply to all the different engineering disciplines. You know, mechanical engineering, electrical engineering, software, structural, security, safety, resilience, and so on. They all, and you know, some of the common practices are they all have to have requirements. They all really need V and V. They all separate what we're trying to achieve by the system from how we're going to achieve it. And that you do the what before the how. Those are all common practices, and those are what makes systems engineering because they apply across the board. It makes sense for there to be a single common approach that is applied by all of the engineering disciplines, and that does not diminish their value. They're all incredibly valuable. They all have wisdom that is important. They are not degraded at all by the systems engineering practices being captured. The same can be true of the subgroup of loss-driven disciplines. It turns out security, safety, resilience, and the others have common practices, and what we are doing in the LDSE project is identifying and capturing and formalizing those practices so that the loss-driven disciplines can be better integrated and they can share, they can take advantage of the synergy that exists between them. And I would like to point one thing out. I talked about it a little bit earlier, the fact that most systems engineering is focused on the needs of the stakeholder. The truth is all of these are needs driven, but those under the loss area are also loss driven. And that leads to one thing that's kind of unique about the loss driven practices and especially the loss driven requirements, and that is they tend to be derived requirements. And this is where I think we're going to be contributing some real value. Derived requirements are those that are not stated explicitly by the customer or stakeholder, but are inferred or generated from the higher level requirements, constraints, standards, or the design itself. They frequently do not come from the stakeholder. It's up to the systems engineer to infer them from the various aspects of the system and the system purpose and the system design. And so that's an interesting area that needs to be pursued. What are some of the key concepts of LDSE? I've mentioned the terms again. I'm going to give you a graphic again. Assets are by definition something that is of value. And so an asset has a value. The value is an attribute of the asset. And that value is judged by what the stakeholder wants. So the value is something that is valued by the stakeholder. And just like with resilience, adversities can degrade that value. And now we come to LDSE. The loss-driven aspects of the system design are those aspects that can safeguard that value. And the whole purpose of LDSE is it facilitates a high-quality, loss-driven system design that can safeguard the value of the assets for the stakeholder when they're faced by adversities. This is the conceptual foundation of loss-driven systems engineering. And it leads to the natural language LDSE requirement pattern. System design shall safeguard the asset and achieve an asset value metric when facing adversity to ensure that the asset value metric meets the asset value metric target. And that's pretty much what it is. Okay, just to mention it, the working groups that relate to LDSE, some are in the analytical enablers domain. That includes resilience, safety, and security. In the application domain, anti-terror, CIPR defense, and healthcare. And in the process enablers domain, risk management and quality management. We have representation of just about 80% of these. Yeah, we don't have anyone from anti-terror or healthcare or defense, and we're going to try to correct that in the near future. This is odd. Okay, this slide isn't building properly, but we can live with it. I'm going to talk a little bit about the LDSE processes that we've discovered and documented. And they're a little bit different. Well, no, they are different from the processes, the technical processes you'll find in the Systems Engineering Handbook or ISO 15288. And that's because these do tend to be derived requirements. And so you don't follow the classic life cycle of starting with an interview of the stakeholder and finding out what their needs are, what the business process needs are. These are things that come from a slightly different direction. And let's just walk through them a little bit. First of all, you want to identify assets of interest that are potentially affected, and that could mean harmed or safeguarded by the system. You need to identify the potential loss types. You need to determine the level to which it is incumbent on the system to safeguard these assets. You need to establish asset loss limits. You need to identify adversities, and these can be conditions, events, things, or whatever, that could cause loss of the value of the assets. You need to identify system vulnerabilities that could lead to loss, consider interoperating systems, nudge the stakeholder toward acceptance. This is an interesting one. Normally, when you're building a system, you're building the system to deliver capability, and the capability is something that the stakeholder desperately wants. You don't have to convince them that they want it. They want it. I mean, they are the fountainhead of why you're doing it. In the case of loss-driven capabilities of the system, the end user, the stakeholder, may have no idea why you want them. Some are obvious, like safety, but you can come up with resilience and security requirements, and the stakeholder might say, hey, I don't have any need for that. And this is an interesting area where the engineer may have to be the trusted advisor and mentor of the stakeholder and educate them on why they really do need resilience or security or availability or maintainability. And as a matter of fact, in our handbook, we have an entire section where we talk about how do you justify loss-driven capabilities to the stakeholder. And in addition to that, one of the ways you achieve that is by picking the right stakeholders. And so let's say you're talking about resilience. You may want to make sure that someone from the stakeholder company who is an insurance expert or a legal expert are included in the stakeholder population, because they will understand why you want to reduce loss. And so one of the ways that you achieve acceptance is by actually making sure you have stakeholders who understand loss-driven concerns. And that's not your average stakeholder. That's something that makes LDSE a little bit different from your normal systems engineering processes. You need to then generate loss-driven requirements, engineer safeguards using design architecture and operational techniques, and then manage risk and establish loss-driven change management and regression analysis during operations. And by the way, yeah, this is another place where loss-driven concerns are different from what you'll see in the normal life cycle. In the normal life cycle, risk management is, well, I mean, if you look at the Systems Engineering Handbook and the CBOC, risk management is almost totally targeted at the project risk, the management risk, reducing risk to the cost, the schedule, and the delivered capability. When you're talking about loss-driven risk management, you're really talking about operational risk. How do you reduce the risk during the production and utilization of the system? And that's something that's not well covered in the handbook or the CBOC, and that's something else. That's another gap that we're going to be filling. Okay, this will be my get off the stage slide. One thing that we're doing that is, I think, really interesting is we are intentionally developing our handbook in a form that it can be digested by a large language model AI tool. And the way this works, on the left side at the very bottom, you see the LDSE handbook. That handbook is basically a compilation of the methodologies by which you perform loss-driven systems engineering. What we've also done is created a standard LDSE assessment prompt. And the prompt's only about a page and a half long. And that would be the prompt that you feed into the large language model. That prompt, you do have to give it some information about the system of interest. What is the system? What are the interacting systems? What are your objectives? If you know anything about the adversities, tell me about them, and so on. We modify the standardized prompt, feed that into the LLM, and then most of these LLMs allow you to attach a document or documents. We, in the assessment prompt, specifically say that the LLM shall use the LDSE handbook as its primary knowledge base in performing an LDSE assessment. And this works surprisingly well. We've done a lot of test cases. There are places we need to improve it. This is still work in progress, but the output really impresses me. I wasn't very optimistic when we went into this, and the results we're getting are really good. What comes out of the LLM, even if you don't enter into a dialogue, and of course in the real world you would enter into a give and take dialogue with the LLM, but it can identify the potential assets of interest, the adversities, potential losses, the mitigation techniques that should be considered. It will write requirements for you. It will tell you how you should allocate the issues that need to be addressed between security and safety and resilience and availability and maintenance and so forth. Really does a lot of deep research and a lot of footwork, and interacting with a talented engineer, you can get a really good product much, much, much faster. But The LDSE assessment needs to be treated as a draft. The LLM needs to be, in my humble opinion, treated like a junior engineer. You know, you don't, that might be a brilliant and energetic person, but you've got to, the engineering community knows how to work with junior engineers, how you have to review their work and mentor them and correct their mistakes, but they still provide valuable input. And that's the way the LLM seems to be. That's the way I think it's going to work out for how we'll end up interacting with LLMs, at least in the near term. Let's see, just wanted to point out there is an LDSE info sheet out there. I think if you search for it on the INCOSE site, you can pull it up. It provides a one-page explanation of what we're all about. There was an LDSE Insight issue, December 2020. The entire issue was dedicated to the concept of loss-driven systems engineering. Here are some references and contacts. And that is all I had. Well, first of all, I want to thank you for your time and attention, and I would be glad to try to answer any questions that you might have.
Thank you, John. That was a really good presentation. I'm very interested, and I can't wait to share this with my coworkers. I work in an environment where we have quite a diverse markets, customers, applications, and resilience is something that it varies with the different applications and customers. So, for example, we have situations where, particularly safety critical situations, where the customer only wants solutions with high confidence. Otherwise, turn it off. They don't want a solution. We have other customers that would rather have a poor solution or a solution with low confidence than no solution. So
Yep.
they're quite opposing requirements, and so we really need to assess each customer use case. Requirement solicitation becomes a big thing, and so if it's two different products, that's fine. Cater it to your customer. If we're trying to deliver the same product to two different needs like that, it presents a little more of a challenge, and we need to design maybe some variability into our solution. But yeah, this is you've stimulated some good thought here. I appreciate it. We do have some questions. I know
Great.
Ivan Taylor put a couple in the chat.
Uh-oh.
Ali has his hand up. Before I go to you, Ali, I'm going to take Ivan's actually his second question. And he said, "Hey John, maybe it would be good to differentiate LDSE from normal risk mitigation activities." Maybe I'll let you speak to that first, and then we'll go to the other questions. So differentiation between LDSE from normal risk mitigation.
Well, normal, boy, I've got to be careful. The difference between risk management, let me do it that way. The difference between risk management and LDSE, and they overlap a lot. And this may get to Ivan's point. Risk management really is more about how do you manage the risks? How do you identify them? How do you keep track of them? You identify triggers that may cause the risk to become a reality. But you do something, you make a decision about in risk management about how to allocate or disposition the risk at hand, and you can accept it, or you can insure it, or you can transfer it, or you can mitigate it. And so mitigation is one part of the overall risk management concern. And when you're talking risk management, the truth is, in most cases, the mitigation strategy and process is a black box. You're not taught about, okay, how do you figure out how to mitigate? LDSE is all about both finding the potential loss and figuring out how to engineer an effective mitigation of that loss. And so LDSE is more on, it is heavy in the mitigation side. It's at the discovery side and the management side. And I would argue that risk management is more the discovery of potential issues and then the disposition, but then it doesn't give you that much advice as to how to mitigate. And that's because it's more a management issue than an engineering issue. LDSE is more an engineering issue. Risk management is more a management issue. And I don't know, I'm kind of, tap dancing here, but I think, but they're both important. And so it's not an either or, you need them both. And as a matter of fact, within our process, we do talk about the disposition of, are you going to accept a loss? Or are you going to insure a loss, and so forth? So we're stealing from the risk management people in that regard.
Mm. Oh,
I don't
thank
know.
you.
Yeah, and Ivan, if I didn't scratch the itch, let me know.
Yeah.
Ivan Taylor. We got
Well,
too many Ivans.
yeah, we do. Well,
Yeah,
we'll come back. Ivan's got another question, so we'll come back to him in a moment and maybe take this answer further. But first, let's go to Ali. You've got your hand up. And yeah, we're a small enough group. Let's just unmute and we'll go to Ali and then we'll come back to Ivan Taylor.
I'm going to actually continue this conversation because this was my question too. So I come from the space sector and I worked in safety. And for me, a lot of what you were talking about also connected with the type of hazard analysis we did. And you're right that some risk is managed externally from a project management perspective, but we would manage technical risk too. So for me, there was a bit of an overlap, first of all, between this resilience aspect being a separate thing versus being considered in the context of safety and existing systems engineering practices. As an example, a lot of the type of things we do it in environments that are harsh. And obviously, we have to survive that environment and we have to maintain particular amount of information being sent from the whatever payload we have on board, right? So that's kind of resilience in our context. But my experience, at least in that field, was that we don't really think of it as something separate from our existing system. Maybe that's different in other disciplines, and that was the question I was going to ask. So is it common in areas like energy, for example, to kind of take that separate and look at it separately from safety and standard systems engineering?
I can tell you from my experience that, and this was at MITRE, which is a pretty advanced systems engineering organization. We had our security experts, and we had our safety experts, and we had our resilience experts. And being good engineers, we figured out we needed to work together. But these were separate people who had wisdom and specialization and deep knowledge in each of those three areas. And our objective with this LDSE is to help those brilliant people with incredible deep knowledge figure out where they should be working with each other. For example, I really think there should be a single set of loss-driven requirements, not three different buckets, but a single set, and they all are traded off against one another. And many of them will be both resilience requirements and safety requirements and security requirements. And so they should be tuned by all three of those experts to come up with one exquisite requirement that satisfies all three. So I don't know if that addressed your question, but that's the direction we're trying to take. And so the ultimate separation, whether they are totally separated and siloed or whether they work together, we're trying to get them to all work together effectively at the level that they should.
John Burtis, Ken Curitan here. Can I stress what you just said? That's why I had my
Certainly.
hand up. and that is don't treat them as separate entities. Then you get into the silos and stovepipes, and you discover that they're doing a lot of work in parallel. When working together, you get better results. The point comes down to, can't we take the beautiful work done by each of those areas, all of their tools and techniques, and leverage them in a common way?
And by the way, just to add another thing, one of the sections of our handbook, we've been accumulating all the different tools and methodologies that apply to these different domains and creating a single punch list. So there's STAMP coming from the safety community, and hazard analysis coming from, well, that's from the safety community, and so on and so forth. And we've got about 50 or 60 of these techniques and tools that have come from all the different areas, and most of them can be applied to all the loss-driven areas effectively.
But you have to take them all into account, and there's trade-offs. And I think
Yep.
that's a good segue into Ivan Taylor's first question. So, Ivan, if you want to unmute, I could read it out, but I'll let you speak to it, Ivan.
Yeah, John, unfortunately, I got a little bit distracted during your talk. As soon as you mentioned do no harm, I immediately got distracted, and I started, saying this is just not right. Because actually what happened was there was an insight issue, I think was on social systems. And one of the articles that I peer reviewed was on do no harm. And I basically said this is not right because everything has trade-offs.
Right.
Everything has opportunity costs. So there's always going to be harm. So for example, even if you do LDSE, you're making a decision about doing that rather than doing something else. And maybe there's a cost to doing LDSE that affects the budget. And so that's a cost. And maybe by spending the money on LDSE, you're not spending it on another requirement that the stakeholder might want.
Yeah.
Hey,
So
Ivan, Ken Kiritan.
Ivan, you're absolutely right. You caught me. I've been trying. Let me tell you the reason that phrase got in there. Your assets they're frequently outside the system itself, but they can be within the system. The system itself can be an asset that you want to protect. Adversities can and usually come from the environment of the system, but they may come from within the system. And what I was trying to capture is the idea that dangers that come from the system that can affect an asset outside the system are part of what we're trying to address. And so I picked the do no harm phrase. And you're absolutely right. I shouldn't say that because it seems absolute. I should say do no unacceptable harm because everything is a trade. You're spot on, and I will clean that up.
John Burtis, Ken Kiritan, may I make the
Yes.
simple observation? The medical term is first do no harm. It's not do no harm on itself. It's a prioritization. That, I think, helps to address Ivan's concern. So just change it to say first do no harm.
Yeah.
Vicky would agree.
I'll clean that up. I'll clean that up. Thank you, Ivan.
You're welcome.
Maybe I'll get rid of the do no harm and just say safeguard assets.
Yeah, I think saying less is more.
Yeah.
Possibly. It's a balancing act, right? It's trade-offs. It's all trade-offs.
Always. Thank you.
Pablo, Mohammed, it'd be really good to hear from you. If do either of you have any questions or comments, or even experiences along these lines? Or anybody else with questions or comments?
Okay, well, let me just mention that we will be holding meetings on this subject at IW 26 next Monday in Torrance, California. And if anyone is there, we're having an open session at 11 a.m. on Monday. And I'd welcome the attendance of anyone who attended this.
Okay.
Yeah, maybe we could send that out to the membership if you have a link, John, that you can.
Yeah, I'm still waiting to receive the link. Supposedly they're going to set up a Zoom capability and give me a link, and at that point I'll make it available to folks, and we'll try to get that out.
Oh, that'd be good. Yeah, I'll reach out to you, John. If there's the possibility of dialing in over a Zoom link, I would be very interested. And regardless, I'm going to reach out to you with my contact info so that we can meet up when you and your wife come through Canada this upcoming summer.
And by the way, I've got to make, oh boy, this will get me in trouble. I have not detected any Canadian accent.
No.
You guys talk. I'm from Chicago, and yeah,
Okay.
you could all.
There's no distinctive accents.
You sound like
John,
Chicagoans.
You should have heard Ivan at the IS. He did
really?
his opening announcement in Canadian, and it was hysterically funny.
You mean Canadian A?
Oh, that's good.
Yeah. But hey, thanks again for the opportunity to share this material.
It's been fabulous, John. Much appreciated. This is a great topic on its own, and the fact that it leads into our next presentation on February 10th makes it even that much better. Yeah. But I am going to put this to use at work tomorrow morning.
Right.
I absolutely, and I'll check in with you later. I think it's always nice to get that feedback of how practitioners are using this.
Oh yeah, yeah, I'd love to hear your experience.
Absolutely, yes. So thank you once again, one and all, particularly John for presenting, but for everybody that is in attendance. And for those of you that may not be here in the call today, but are viewing this as a recording on the INCOSE Canada chapter website, thank you all. Have a good evening. I'm going to stop the recording and bid everybody a good evening. And we'll see you on February 10th. Thank you.
Good night, everyone.